This is section 7.2, which now involves volume and the disk method. In the previous lesson, we talked about the area of a curve. Now we are going to talk about the volume. So here, it's important to try to visualize what the object ends up looking like, and that can be kind of challenging. So what we're going to do is we're going to start off with some object or some solid. So in this case, we're going to have this rectangle here, and we're going to take this rectangle and we are going to revolve it about this line, which is called the axis of revolution. If I take this rectangular object here and I revolve it about the axis of revolution, it's going to end up giving me a solid object in the shape of a disk. So think of it as like if you're cutting an orange into slices, it's going to be like a disc, like a frisbee type looking thing. So if I want to find the volume of this, the volume of a disk is found by taking pi r squared times the width. And that is shown to us right here. So let's analyze this a little bit more. The volume of this disk, which we talked about before, is the area of the disk. So that's just the area of the disk, which is pi r squared. Okay, so the area of a circle is just pi r squared, where the radius is r, times the width of the disk, which is represented by W. So this formula is going to be very helpful to us. So let's say that we are interested in this area in blue here. And what we're going to do is we're just going to take a representative rectangle, which is going to be here, because really I can split this region up into multiple rectangles, and these rectangles added all together will be this region. So if I take this rectangle and I revolve it about this axis, as we can see here, if I spin this around, I'm going to get this disk as shown here. Well, if I take another disk and another disk and another disk over and over and over and keep revolving them, I'm going to have all these different disks in here. And really, I want to work toward an infinite number of disks. And we'll get to that shortly. But here, taking a small step, here's my representative rectangle. If my rectangle is perpendicular, let me change colors here. If my rectangle is perpendicular to the x-axis, all of my work is going to be in terms of x. On the other hand, if my representative rectangle is perpendicular to the y-axis, everything will be in terms of y. And that's important to recognize and take note of. Now, again, I'm going to have lots of different representative rectangles, and I want to add them all together. So if I add them all together, I'm going to end up getting the volume of a solid, and it's going to be an approximation. And that approximation can be written as a sum. But I want that to be exact. And if I want that to be exact, I'm going to take an infinite number of rectangles, and that will give me my integral. Now remember, the volume is pi r squared times the width. The width is the change in x. Okay, so you could see that on the previous slide. All right, so moving on, this ends up being what we are working towards. Now let's kind of talk through this a little bit. If I have a sum of all these rectangles times pi r squared dx, or delta x, and I integrate that, remember that pi is just a constant, so you can move pi out. Everything is in terms of x, so instead of writing delta x, we're going to represent that as the change of x, or dx, and we're going to write r as r of x because it's a function in terms of x. So our formula is this, and you can see the progression that we have taken to get there. So this is the formula you always want to remember, where r of x represents the radius. Okay, we have a little more to build on before we can see some examples. So let's look at the next slide. Okay, we've already kind of talked about some of this, so I just want to reiterate. This is called the disk method because when we take this representative rectangle and revolve it, it looks like a disk. So we have a horizontal axis of revolution. That's when everything is in terms of x, when we revolve about the x-axis. And we also have a vertical axis of revolution. That's when our rectangle is revolved about the y-axis, so everything is in terms of y. The limits of integration and everything. Notice our rectangle is perpendicular to the x-axis here and perpendicular to the y-axis here. So these volume formulas are going to be very helpful. So make sure that you remember those. I think we're ready to get into an example, so let's take a look at example 1. In example 1, it says find the volume of a solid generated by revolving the region bounded by the graphs of the equations about the given line. So here, if this is telling us all these different functions and we are revolving about the x-axis, that means we are going to take our object and go around the x-axis. And so this is telling us that everything's going to be in terms of x, and I'll illustrate that here in a moment. But just like in section 7.1, the first thing we want to do is sketch a picture of this. When I sketch a picture of this, I should know what this looks like. It's just a sketch. It's going to be a parabola that opens upward. Y equals 0 goes through the y-axis at 0, which really ends up being the x-axis here. And then we have x equals 2, which is this line here. So we can see that this region here is the one of interest. This is the region that we are going to take and revolve about the x-axis. So I'm going to take this and I'm going to go around and around and around and around the x-axis. And when I do, I end up having this region here. It becomes a solid object, and kind of think of it as a top shape or kind of like a tornado shape. So you want to kind of visualize what that looks like. And remember, what we're going to do is we're going to take an infinite number of slices and we're going to slice it, slice it, slice it. So if I'm slicing a top, I'm going to get all these different discs. And remember, we are going to make these slices perpendicular to the x-axis, since that's our axis of revolution. Whatever our axis of revolution is, our slices are perpendicular to that. So this is going to be, I'm going to have this slice here. This is going to be my radius. So I need to identify what this radius is, and that's where the top minus bottom information from the previous lesson is helpful. My radius is going to be top minus bottom. So I need to identify what the top minus the bottom is in this function. The top function is 2x squared. The bottom function is just 0. So my radius is 2x squared. That is in terms of x, which is great because we know everything needs to be in terms of x. So remember, I'm going to find the volume by taking pi times the integral from a to b of the radius squared dx. So plugging this in, I find that I'm going to integrate the radius, which is 2x squared squared dx. Now the only thing that I'm missing here are my limits of integration. Well, we can see that our shape ranges between an x value of 0 to an x value of 2. Okay, so those are going to be my limits of integration. Now the hard part is setting this up. That part is done. So now we end up having, when I square all of this, I end up getting 4x squared dx. So if I want, the 4 is a constant, I can move that 4 out with the pi, and then I'm simply integrating x squared, which is a little bit easier. You certainly don't have to do this, but we end up getting, let's see, what do we get? Oh, I made an error. I apologize. This exponent here should be a 4. Hopefully you caught that. Sorry about that. So when I integrate then, I end up getting 1/5 x to the power of 5. And we're going to evaluate that from 0 to 2. So 4 pi, oh boy, 4 pi times 1/5 2 to the 5th minus 1/5 0 to the 5th. You should recognize that this goes away. So we have 4 pi times, this is 32 fifths. So we get 128 pi over 5. If I put this over 1 and multiply across the top, across the bottom, I get 128 pi over 5. I prefer leaving everything in terms of pi to make life easier, but if you want to write it as a decimal, go for it. Now, this is the only example that I'm going to do with the disk method. So if you want to see more examples, remember you can go to Calc View and watch some more examples. Now we get to what's called the washer method. This is the exact same thing. The difference now is our shape doesn't necessarily touch the axis of revolution. So if I take my rectangular shape and revolve it, I'm going to end up having some space in between. And so this is going to end up looking like a disc, or kind of like a donut, if you will. So if I have something that looks like this, and you know this radius, you can find the area of this by taking this big radius and subtracting out this little radius, right? I can subtract that out. So that's what's happening here. If I want to find this area, I'm going to take the big radius minus the small radius to get the area of the donut, if you will. Okay, so that's what happens when we have the washer method. I'm going to take the big radius, or the outer radius, minus the inner radius when finding the volume. Everything else is the same. Now, it's important to notice this formula here. This is big R squared minus little r squared. That is not the same as the quantity big R minus little r. So make sure you are comfortable with that difference. Let's take a look of what this looks like. Okay, so in this example here, my area is this little blue area here, and we're going to revolve that about this axis. Now, sometimes it's helpful to draw in the reflection, which is often very difficult for me, but it's going to look something like this. So if I revolve this shape around and around and around, it's going to end up looking something like this here. And they have the reflection drawn for us. So if I'm looking at this, it's helpful to identify what the inner radius is and what the outer radius is. So looking at this, the inner radius is going to be the distance from the axis of revolution to the object, the inner portion of the object. This is going to be the inner radius, or little r of x. On the other hand, the distance from the axis of revolution to the outer part, the outermost part, that is going to be big R of x. So find little r of x, find big R of x, and then you can just plug it into the formula that I'll show you here. So once you have identified big R of x and little r of x, you should know that this is the outer radius minus the inner radius. Oops, it should be inner. And you're going to square those individually and then subtract. Okay, and everything else is the same. If we are perpendicular to the x-axis, things are in terms of x. If it's perpendicular to the y-axis, things are in terms of y. Okay, so let's take a look at some examples. Okay, so here, this is the same graph that we had. Did we do that? Yeah, same graph we had before, I think. So I'm just going to sketch this real quick. We should know what 2x squared looks like. And y equals 0 is here. And x equals 0 is, I'm sorry, x equals 2 is here. So we have this shape here. Okay, now the thing to pay attention to is that we are going to revolve this about the y-axis now, and this makes the difference. Before we revolved about the x-axis, so we had a disk, but now we're revolving about the y-axis. So if I were to draw in my reflection, it would be this here. So I'm going around and around and around the y-axis. So this kind of looks kind of like a bowl in a way. Okay, so if this is a bowl, I need to be able to tell that I have an inner radius and an outer radius. So what I need to do is I need to find big R and little r. Now, these have to be perpendicular to the axis of revolution. And this tells us that everything is going to be in terms of y. So let's analyze this a little bit. Remember, r is going to be our inner radius. So that is from the axis of revolution to the innermost part of our graph. This is r. So think of this, since we are dealing with y, think of this as right minus left. Our right function is this. It's this 2x squared. But I don't want to use 2x squared as the function because it has to be in terms of y. So if this is 2x squared, remember this has to be in terms of y. So I need to get x by itself. So I'll divide by 2. So x squared is equal to y over 2. And then I'll take the square root of this. And remember, technically there should be a plus or minus. So x is equal to the square root of y over the square root of 2. Okay, or you can simply write it as the square root of y over 2. All right, now I'm only interested in this positive part, so that's why I've omitted this. And again, everything needs to be in terms of y. That's why I rewrote this function. So this is the function that I'm going to be using for my inner radius. I now need to identify my outer radius. Now the outer radius is the distance from the axis of revolution to the outermost portion of my graph. This is big R. So again, right minus left, this is 2 and this is 0. 2 minus 0 is simply 2. So that's a lot easier in this case than finding the inner radius. So now I can go ahead and find my volume equation. So remember, it is pi times the integral, and pi is involved because these washers are still circular shapes. So that's why our area is pi r squared still. Now we're going to take the inner radius squared, the outer radius squared, which is big R squared, minus the inner radius squared, and then dy. Now notice my integrand is in terms of y, just like we wanted it to be. We don't want to plug in this here because that is in terms of x. So I simply get x by itself right here and plug the y value in. Now I need to identify my limits of integration. My limits of integration are going to be from here, because everything's in terms of y, which is 0, to here. And I need to find what that value is. Well, remember, that is the intersection of these two functions. So whenever x is 2, I can find what y is. When x is 2, y is 8. So this intersection is 2, 8, and we need the y value. Okay, so moving on to simplify all of this, I have pi times the integral from 0 to 8 of 4 minus, when I square this, I simply get y over 2, or let's write this as 1/2 y. Square, just 1/2. Just 1/2 y, yeah, dy. And now I can integrate all of this. And when I integrate this, I have pi times 4y minus 1/4. This should just be a y, I'm sorry. When I integrate this, I have 1/4 y squared. Now, evaluated from 0 to 8. If I plug 0 in, this all goes away. So it's really just plugging in the upper limit. So 4 times 8 minus 1/4 times 8 squared. Simplifying this, I have pi times 32 minus 16, which gives me a volume of 16 pi for the final answer. Now, as we move forward, I am just going to set up the integral and give you the answer, because you should be able to integrate these by this point. Now, sometimes our axis of revolution is the x-axis, so we'll revolve about the x-axis, and sometimes we'll revolve about the y-axis. But there are also occasions when we may want to revolve about a different line, say y equals 8 in this case. Now this is the same exact graph that we had before, just for simplicity's sake. So I'm going to sketch it again. Okay, so it is still the same region that we're interested in, but now we have a completely different axis of revolution. So if I want to revolve this, I am going to revolve through this point of intersection, which we found in the previous example. So now I'm going to take this and I'm going to revolve about this axis. Now, if I'm revolving about this axis of revolution is perpendicular to the y-axis. Since this is perpendicular to the y-axis, I am going to be in terms of x. Okay, so this is parallel to the x-axis, which means it takes the same idea as if we were revolving about the x-axis. And if we revolve about the x-axis, everything is in terms of x. Okay, so looking at this, okay, so we have this region here. If I draw in the reflection, it's going to be this. So I should be able to tell by looking at this that there's a hollow part. If there's ever a hollow part, we are going to be using the washer method rather than the disc method. Okay, so if there's a hollow part, it's a washer. We know we're in terms of x. So if I have a washer, I need to find the inner radius and the outer radius. So let's do that now. Now my axis of revolution is here. So from my axis of revolution to the inner portion gives me r. So think of this as top minus bottom, or bottom, top minus bottom. The top function is this value here, which is 8, minus my bottom function, which is this curve, which can be in terms of x. Okay, so little r is this, top minus bottom. Now let's find big R. Big R goes from the axis of revolution to the outermost portion of our function. So if I do top minus bottom, the top is 8, the bottom is 0, so this is simply 8. So I now know big R and little r, and I can set up my integral. It's going to be pi because this is a circular shape. Big R is 8, so 8 squared minus little r, which is 8 minus 2x squared, dx. Now I need to identify my limits of integration. Everything is in terms of x, so I'm going to integrate from 0 to 2. So my limits of integration are 0 to 2. Now the hard part is done, which is the setup. Now one thing I want to mention before I go on to the next example is you cannot distribute this square because you have a binomial here. Remember, you can only distribute an exponent if the base is involving multiplication or division. So here you will want to FOIL this out. FOIL that out, square this, and when you simplify this, you should, this is 0, you should get negative 4x to the 4th plus 32x squared. If you want to pull out a GCF, you can. When all is said and done, you should get 896 pi over 15 for that volume. Let's take a look at another example that revolves about a line other than one of the axes. All right, so we have the same region once again, and this was chosen simply for simplicity purposes. Okay, so we still have the same region. Okay, now we are going to revolve about the line x equals 2. Now x equals 2 is this line right here. So we are going to take this region and revolve it about this axis. So I'm going to take it and revolve, 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 revolve. This is the reflection. So once again, I have something that looks like a top. This whole region is solid. There isn't a hollow part. So if the whole solid is solid, then this is going to be the disk method. There's not a hollow part, so it's not washer. Now, our axis of revolution is parallel to the y-axis. So since this is parallel to the y-axis, everything is going to be in terms of y. So that means, remember before, when I got this by itself, I need to get, if I want this to be in terms of y, remember I get x by itself, and we found that x is equal to the square root of y over 2. Okay, so that's important. So I have the disk method, and so if I'm dealing with the disk method, I'm just going to have one radius. So the radius is going to be from the axis of revolution to the outer portion of our function or our graph. So this is the radius. So if I take my radius, I'm going to do right minus left here. So if I take the right function, that's 2 minus the left function, which is the curve, the square root of y over 2. So that is my radius. So I can go ahead and set this up. My volume is pi times the integral of the radius squared, which is this. So I'm going to have 2 minus the square root of y over 2 quantity squared dy, because this is my radius. I now need to identify my limits of integration. Since we're dealing with everything in terms of y, I will integrate from 0 to this y value, which we found in a previous example to be 8. Now, just like we saw before, I can't just distribute this square because I have a binomial here. So I'm actually going to want to FOIL this. And when I FOIL this, I'll help you out with this. I'm going to end up having 4 minus 4 times the square root of y the square root of y over 2, because I will have the inner, which gives us 2 times that radical, and the outer, which is 2 times the same radical, so I'll have 4 of them. Plus, when I multiply these, remember a radical times itself is whatever is underneath the radical. Okay, so this here is what I will end up with. Now you might want to rewrite this as 4 times y over 2 to the 1/2 power. That might help you a little bit. And with this, okay, so with this, you can look at this as 1/2 times y to the 1/2 power, which is 4 times 1/2 to the 1/2 times y to the 1/2. Well, this is just a radical. Okay, so you can write this as 4 times the square root of 1/2, y to the 1/2. And then this is the square root of 1 over the square root of 2, and then you can rationalize. So this is just root 2 over 2. So you have 4 times root 2 over 2 times y to the 1/2. Well, the 4 and the 2 simplify, so this is 2 root 2 y to the 1/2. And that is what you get to integrate. That will be a lot of fun for you. When all is said and done with this integration, you will have 16 pi over 3. If you need help with this integration, just let me know. Now, in the previous examples, we had to find the object. But there are cases when the solid object is given to us and we need to find the volume of it. So with the disk method, we can find the volume of a solid having circular cross sections by using this here. Now, we can really find the area or the volume of any shape, not just circular shapes. So maybe our cross section will be squares or rectangles, triangles, circles, so on and so forth. So we have a lot of different shapes that we can analyze. And here's what I'm talking about. Let's say I have this solid shape and it looks like this. The solid shape is given to us, so we're not making any revolutions anymore. Instead, what we're going to do is we're going to take this solid and we're going to slice it, slice it, slice it an infinite number of times. And if I take one of those slices and hold it up, it could be any shape. It could be a triangle slice. It could be a square slice or a semicircle, all these different slices, okay, or different shapes. And what I want to do is I want to identify what type of shape that cross section is. So what shape is the cross section? If I can identify what shape the cross section is, I want to find the area of that. So if the cross section is a triangle, find the area of a triangle. If the cross section is a square, find the area of a square. If it's a semicircle, find the area of a semicircle. And then if you know that area, you integrate it. And that's it. So now notice that when we are finding the volume of solids with cross sections, please notice the absence of pi. We don't have a pi there unless our cross section involves a circle or a semicircle, because the area of a circle or a semicircle involves a pi. Okay, now remember, if our cross sections are perpendicular to the x-axis, everything is in terms of x. If our cross sections are perpendicular to the y-axis, everything is in terms of y. Now I'm only going to do one example of this, so if you need additional help, please let me know. So here is this example, and we want to find the volume of the solid shown right here. So this is like a cone, if you will, or not a cone, I'm sorry, a pyramid. So it tells us that the base of the solid is the region bounded by these lines here. Okay, so it's telling us that our base is bounded by f of x, which is this line here, and g of x, which is this line here. So this is the base. Okay, so this is the bottom of this. Okay. Now, our cross sections are perpendicular to the x-axis, so that means everything is in terms of x. We are also told the shape of these. They are equilateral triangles. So I need to be able to find the area of an equilateral triangle. Now, some of these bases, you might need to look up what this formula is. Now, if this is an equilateral triangle, I'm going to tell you that the area is found by taking the square root of 3 over 4 times the base squared. Now, if you don't know that and you're like, oh my gosh, I'm not going to do well, I totally don't know, don't worry, just look it up, okay? You will see that these bases, these shapes they're all gonna be the same ones over and over, okay? So I need to figure out this area. If I find this area, I can just plug it into my formula and I'm good to go. Okay, now remember, the volume is going to be the integral of a of x. Okay, so let's analyze this here. Okay, so if I want to find the base, I want to find the area of this triangle. Okay, so I need to figure out this base because then I can just plug that base in there and square it. So it is the same thing. I want to find this, and all I do is I find the top minus the bottom. So the base is found by taking the top function minus the bottom function. So if I want to find this, the top is f of x, or in this case, 1 minus x over 2. Minus the bottom. The bottom is g of x, in this case, negative 1 plus x over 2. So I can distribute this negative, and when I do and simplify all of this, I find that my base is simply 2 minus x. And I will plug that in here. So my area is root 3 over 4 times 2 minus x quantity squared. We've seen this a lot before. We can't just distribute that, so I need to take this times itself and FOIL it out. So I get root 3 times 4 minus 4x plus x squared. This is the area, all of this. So I'm going to plug this in here to my equation. So my volume is the radical of the square root of 3 over 4 times the quantity 4 minus 4x plus x squared dx. Now, I need to identify my limits of integration. Everything is in terms of x, and my base is in between an x value of 0 and an x value of 2. So whatever my base is between are my limits of integration. Now I integrate this, and that's something you should be able to do. It may be helpful to take this constant and move that out. So you'll just integrate 4 minus 4x plus x squared. Okay, and when you integrate, you should end up with this. And you are going to evaluate this from 0 to 2. And when you do, and you simplify everything, you should get 2 root 3 over 3. And that's it.